and he's a fellow of the ASME, and he received many awards, including the ASME Outstanding Young Professor. Okay, Dr. Zhang.
Thank you, Dr. Ryu. Hello, everyone. Today I'm gonna present on AI powered smart manufacturing for small and medium-sized manufacturing companies. So when you go to small and medium-sized manufacturing companies, it's not only SMMs, but manufacturing companies now. What they're trying to do is.
It's okay.
Okay. So I guess the mic is not on, or can you guys hear me in the back? Okay. So a lot of times they're trying to get data from the machines. So in order to optimize the manufacturing process, layout, and planning, getting data is really important. And then once you have the data, then you will be able to develop AI models to be able to monitor the process more, predict what's going to happen, and so on. So there are many applications once you have the ability to get data. But getting data from a manufacturing floor is not as trivial as you may think, right? Because machines are old. Some machines are new, but a lot of manufacturing companies don't want their machines to be connected at all. Because if anything happens, any hacking happens, then if it gets interfered and you have downtime and so on. So there are many different issues that needs to be addressed. So I work in that area, try to get data from the manufacturing equipment, manufacturing processes as well, and how do we actually improve on a real manufacturing floor, right? And also, it's not only the machine that needs to be digitalized, but also humans is also another aspect, right? How do you actually get data from humans, human motions, human work? Also, how do you actually automate what humans do, right? Typically, when you want to automate, you have to set it up for automation. You have to put the parts in an array for the robots to be able to pick it up and so on. But that requires a lot of infrastructure investment. But small, medium-sized companies can't really do it. So can we have a smarter robot to be able to do what humans do, right? So small and medium-sized companies actually need more smarter machines so that you can actually put a robot and be able to do what humans used to do as well. There are workforce shortage happening in the United States. So the need for robots is significant right now. But how do we actually do that, right? They don't have they can't invest the entire automation line for small batch operations and so on. So it has to be really flexible. So how do you actually work, and how do you get the robot to work with humans and things like that? That's the area I do research in. So I'm gonna introduce those two aspects today. So when you get data from machines, right, you can do machine and operation information, right, monitoring. So you just get what is the machine doing. And when I first started going to companies to get to see how much data they're actually getting from the machines, right? No, not really. They don't really get any data. But they want to know what the machine is doing, whether the machine is being used. So they have to utilize, okay, that machine's only being utilized 30%, or you have 70% left. Maybe I can take this order to be able to manufacture that and so on. They need that information, right? But then if you actually go into the manufacturing floor, you try to get data from the machine. Okay, machine may be on, but it may not be actually producing, right? Machines turned on and the operator went for coffee, whatever. It could happen, right? So how do you actually get the real-time, accurate information about the machine? That's actually very important. Also, at the same time, condition-based monitoring, right? Is the machine going to fail? Is the process, is there an accident, anything happening, and so on? How do you actually do that, right? So those are the areas that I'm working with. In order to get data from machines, one simple way is to get the data from the machine itself. Machine controller is Ethernet ready, so you just plug in Ethernet cable, you get data from the machine. You can do that as well. Newer machines, you can get it, but legacy machines, you can't. You have to get the data from the PLC controllers, but no manufacturer wants to touch the PLC lines, right? Because anything can happen, right? So that's one way. Or you can get data from the sound sensors. You can put sensors on, and you can get data from the sensors, whether it is vibration sensors, sound, microphone, or other types of special sensors you can develop and put it on the machine, and so on, right? So, but one of the areas that I'm working with is the sound-based sensors. I'll go over that. But here's an example. This is a CNC machine we have at Purdue, right? We have equipped this machine with so many different sensors. We get data directly from empty connect adapter, basically, which is a standard format, right? You can get data from many different manufacturing company machines, but they're all in different formats. So you can't really communicate between machines. So they have to be converted into standard syntax. That's what the empty connect is. So we use the empty connect standard to get data directly from machines. So these are the types of data you can get from machines, like what's the spindle speed, right? This is a CNC machine, the metal cutting machines. Right? What's the feed rate you can get? Is the coolant on? Is the door open? Is there error message that's happening? You can all get all that information from the controller. These are the sensor data, right? So from the sensor informations, okay, is there too much vibration? Is the machine not in good conditions, and so on? So you can do all of that. So we have this machine. We have put so many different sensors on the machine. We're getting directly from the machine as well, and trying to get a lot of data during the actual manufacturing process, and develop AI models for many different applications. But one of the things that we experienced is that getting sensors, even getting data directly from machine, is not cheap, right? So you want to get you just want to plug into the internet and get data. It sounds simple, but no, you have to have a special software to be able to get data. And the manufacturing machine developers, they actually ask you to pay for that. It's a business, right? And it's a simple connect, but they will ask a few $1,000s for each machine, and that's like per year, right? Sometimes it's one-time payment, sometimes per month, sometimes per year. So it becomes expensive when you have hundreds of machines, and you want to get data. So it does become expensive. You try to put sensors on, vibration sensor on, right? You have to sample at high frequencies. You want to get sample at high frequencies. You need a good data acquisition board. Already it becomes expensive, right? So how do you actually get a low cost? But another thing is that operators know what's going on with the machines usually by sound. When you have an experienced operator, they know everything about the machine with the sound, right? The operator is eating lunch and then hears something. Oh, something happened. He just runs down and exactly knows what was actually going on with the sound, right? So how can we actually utilize sound, right? So the machine is actually speaking to you with all the sound, right? So can we actually figure out what's going on? But one of the problem is that on a manufacturing floor, the operator has to really get close to the machine and listen to it because it is very loud. You get multiple manufacturing machines operating all together. How do you actually focus on one machine, right? So can we develop a sound sensor that can focus on one machine, right? So using sound to inspect the machines has been used quite a bit, right? We have the famous sound inspection by wheel tapping, right? You can inspect. Mechanics use sound to evaluate the initial evaluation for the cars as well too, right? So when you look at the sound, right, like close, when we use the eardrums, how we process the sound, right? We have the eardrum, we have the malleus, cochlea, and so on to be able to process the sound with our brain. We can do the similar things with the sound. Using data acquisition filtering, and then you extract the feature using the sound and then based on the feature, you can figure out what's happening, right? So what I wanted to do was, can I assume the machine is actually speaking, and then figuring out what the machine is actually telling us. But the key thing is, how do we get to hear only that machine? So I got the idea from when I went to the hospital. Doctors listen to our heart using stethoscope of our internal sounds, right? And when you use a stethoscope, you don't really listen to outside. You listen more on the inside of the body. So using the similar ideas, we developed a stethoscope-based, style-based sensor. It's a context sensor that listens to the machine. It's like putting a broomstick on the machine and trying to listen to it. Very similar idea, right? But can we actually do that? So you have a diaphragm on the machine that is vibrating because of the sound that is propagating on the machine. And once you use a sound that is propagating on the machine, you don't really listen to the outside. You're only listening to the machine propagation sound. So we can listen to the machine only. That's what we've been doing. So we have designed and developed that sound, and we started putting on the manufacturing machines. And you actually get the amplification effect when you have the context sensor. So you actually hear it much louder. That's why doctors can listen to our heart, right? When you can't really listen to our heart sound, but if you put your ears on the chest, you may be able to hear it because it is in context. So you get amplification of the sound because of the context. Or you don't get the attenuation of the sound because of the context. So here is an example of our, I don't know whether the sound is working, but so this is a typical manufacturing. So can you guys hear that? So I guess sound is not going to the HDMI cable, but you can hear that, right? That's the typical manufacturing floor. This is a welding machine. So basically what it is, you have a seam welding, right? And then you have two plates going in, and it does the point welding and then continuous welding together, right? But they want to know, the company wants to know how long is the welding, like, how many parts actually produced, how many weldings have been done. And if you can calculate the exact welding time, then you can estimate the wear of the welder as well too. But how do we actually do the exact calculation of that? Right? So you try to listen to the sound of the welding. That's the welding. That's the welding. Right? It's so loud you cannot hear that. But this is the sound picked up by the sensor. Here's the welding sound. You have this small welding sound, you are able to pick it up. So you can actually listen to the machine only. That's the sound that's happening within the machine. I don't know whether you're able to hear that from the back, but so you can see the spectrum of the sound. You can see, here's the welding process. You can clearly hear the welding process using the sensor. So that's what we've been doing. So what we want to do is, okay, how do we get the sound signal, the wave file, and extract the features and develop AI models to find out what's going on with the sound. So in our speech recognition, when we do our speech, and then whenever you use Alexa or Hey Google, right, they will take the sound and extract features from the sound. The typical sound recognition technique uses what's called MAE spectrum. So our cochlea has a series of filters, right? And MAE spectrum is basically is a series of filters that are similar to our cochlea, and then extract features like that. So we use the MAE filter bank is the cochlea filters, and then MAE spectrum is what you get out of that. So we're using that spectrum as a feature, and then feed that into the AI models to develop. So we use different AI models like ANN, CNN, LSTM, or autoencoders to be able to predict or classify what's going on with the sound. So I'll go through some examples of the classification that we have done. So the end goal is to be able to understand what the machine is speaking, right? So you saw the welding process. You have the initial motion of the machine, putting it in, welding sound, and then continuous welding and so on. It's a series of sounds that happens. So it's like a speech, right? So if any of that is missing, then we know there's something wrong with the sound. So if you listen to the machine for the entire cycle and consider that as a sound or a speech, and then there's a little bit of difference in that speech, we know there is some anomaly in the speech as well. So that's what we want to do. How do we actually listen to the machine for a long time and then actually go into different sound segments, figure out what each segment was actually saying. So you can do operation information, running state, operation state, how many parts, which part as well too. Like you have machines that are producing many different parts, and can you figure out, okay, this time it was part A, this time it was part B, because you're listening to the entire manufacturing of the part. So can we actually get that kind of information? Or can we do conditions like machine health, part quality, this part was not produced properly, and so on. So that's my end goal. At the same time, we're trying to apply human skills. Sometimes humans listen better, and then human listens to this and then label it for us. Then we can use that information to develop better AI models and so on. So, so we have a machine using Empty Connect to get data directly from the machine, and then we get sound sensors and try to compare. Is the sound sensor predicting, classifying the same way as the controller is giving you information? Or is it actually, can we get better information from the sound? That's what we're doing. So, and then you have to get the data in a standard format so that you can get data from this machine, that machine, they're speaking the same language, right? So that's what we're doing, making it into a standardized syntax. And this is sort of the framework, entire framework, where we can actually develop 8 different AI models and then use it. So data gets deployed into the cloud, and then you have AI models in the cloud, deploy that AI model into the edge device, and have that edge device be able to classify right away. So we're developing this kind of framework to be able to use that in different manufacturing floors. So here's an example of a CNC machine. It's everybody, I'm assuming everyone knows what a CNC machine is. It's a metal cutting machine, right? And this is an example of a classification, right? Well, as I said, directly from the machine, you get colon on, spindle on, RPM, and all that information you can get directly from machine. But you can't really get it if it's a legacy machine. But can we put a sensor on and get the data that you're getting from the controller similar to what you're getting from the controllers? So this is an example of that. So initially the machine is off, right? And the machine just turns on. You hear the sound, and machine is on. So it's been trained to know which component is just turned on. So you have the mist collector on. You have the coolant just turned on, right? You have the chip conveyor just turned on. You have a composite sounds, but AI model knows which one is actually on and off. You have RPM, spindle at different RPM, right? Change the RPM, and spindle is just turned off, and so on. So you can get simple information like this directly from the sound, right? So you don't need to actually have the some machines cannot have the ability to be connected to the controller. You can just put the sensor, a low-cost sensor, and with the AI models, you can get similar information. This is an example of condition monitoring. So you have a tool, right? And tool is cutting, and then it wears down. And a lot of times you would have to change the tool at maybe 70%, 80% of its life. Right, so you need to change it properly. A lot of times they would actually will not use it to the full life of the tool. Will change it before because you don't want the tool failed that will lead to significant downtime and quality issues, right? So can we actually monitor and know the wear, right? So we just use the sound. Sensor 1 is the microphone. You just put the microphone in the machine. But this is just in the lab setting, so you don't have external noise. So without the external noise, you get 95% success rate with the microphone. With our sensor, you get close to 100%, 98% success rate to be able to tell the machining sound from a new tool or the one tool. In CNC cutting machines, you get chatter, which is excessive vibration that happens. Then you ruin the part right away when you have that much vibration. Can you actually tell that, right? So let me show you an example of a chatter sound. So you're cutting one way and the other way and so on. So you will have a tool coming out. That's chatter sound. That's a normal cutting sound, right? So a lot of times, I see this machine, it's automated, right? So it's cutting normal, and then all of a sudden you can get chatter, but the operator is not there to detect it, and it will just continue to cut, and then you can break the tool. It will lead to part quality issues and so on. So you may need to scrap that part, right? So the detection of chatter is actually quite important in machining. So we have run many different conditions, and then we use the sensor. You can tell this is the microphone again without any external noise. This is our sensor. You can tell chatter. The pink arrow is where the operator said, the experienced operator who used to work at Caterpillar said, okay, that's chatter sound. That's not chatter, right? So that's the pink arrow, right? And then you can tell chatter, no chatter, chatter, right? And no chatter, the difference clearly within the sound that you're getting, right? So these are the prediction results. So with our sensor, that is just put it on the base of the machine, not even inside. You just put it on the base of the machine and be able to listen and predict close to 93% and 91% success rate. That is also, there's some errors because of the operator trying to determine it's not chatter. So we're actually sending the sound to different machinists at Caterpillar and different machine shops. Can you tell this sound whether it's chatter or not? We're getting more data to be able to develop, improve our models as well too. So this is real-time condition monitoring. If chatter happens, can we actually tell? Can we calculate the exact amount of time? If a tool is used, and if you can calculate the exact cutting time, right? The exact cutting time, if you get it from the software, it never matches properly with the actual operation. So can we actually tell exact cutting time and monitor real time? So this is an example of the real-time monitoring. So you do get data from the machine controller. From the machine controller, we can do all the simulation, real-time simulation like this. So the white line is when it's actually doing the air cutting. So it's not really cutting, but it's moving around. So from the sound, we can figure out it's air cutting. Okay, and then you go in and then start cutting. So it's a P that we're machining like this. Now you get green color, which means we detected the sound, and now it's cutting for that path, right? So this is a 2-millimeter tool. Even the machinist cannot actually tell whether it's machining or not because you have the coolant sound going on and so on. It's very difficult to tell. So we are able to listen to it and tell whether it's actually, you can see the red line over there. We changed the RPM slightly to cause the chatter during the machining, right? So you can tell it's an abnormal cut, and you can detect it real time. And then you can see all the green lines over there. That's how long it cut. So you can exactly calculate how long was used to cut that part. So this is a Walter Vision machine. This is on an actual manufacturing company. They have a tool grinder. can we actually calculate, grinding time? One of the things that they wanted to do was we have the machine controller data as well as the sound data as well too. Can we tell how long is the machine being used and compare to the actual, right? So the top is the based on sound sensor and bottom is actually data from the Fanuc controller. Right? You can see it matches for the utilization very well. So just using the sound, we can get the utilization as good as the getting directly from the controller. Here's an example of a welding machine. I showed you the welding process, right? So during that welding process, you have a fixturing, moving, welding, rotating, and manual setting up. You have different stages, right? Can we tell the differences in the sound and find out, okay, here is the amount of time being used for the manual. Here's the amount of time being used part rotations, moving the part, and so on. So we can get the exact cycle time, and we can tell the difference between an experienced and non-experienced operator as well too, and different things. You can see the sound. There's the we have the moving sound. We have the part rotations. So that's the sound from cycle 1 to 1. So I can give you more in detail like this. So you have the plate fixturing, and then you have turntable moving to first welding position. You have the first spot welding. You have the second seam welding, right? And then you have to turn it again, put the new part in, and then turntable rotates again, and so on. So you have number of steps, right? Can we tell? So we are categorizing, okay, idle, manual setup, and actual operation, and idle, right? So knowing the actual operation time is important because that's how the OEE, the overall equipment effectiveness calculation goes to. So we develop AI models to be able to calculate, classify them, right? So this is the algorithm and data flow. I'm not going to get into the details of those, but basically we have built this dashboard saying, okay, for this welding machine, you have, and this is the number of welds, you have cumulative welding counts, you have the cycle time for each operation, and so on. So this is a local company that I'm working with. Went to the company, put the sensor on. We will do these calculations for you. We developed this dashboard, gave it to the manufacturing company, and they were very happy, right? For one, it was free, right? I gave it, it was free for them. And they have like 16 welding machines. Hey, can you put those sensors on all 60 machines and get this kind of data so that they can calculate, right? And then they can use the information for the turntable. You have a bearing that goes bad sometimes, then if you can predict it, right? What about welding wear? Can we actually predict it? So all those things we need to, they want to find out. So what we're going to do is we are going to put more sensors. I asked them, can I use your facility as my research test bed? Can I get all the data and develop different AI models? And fine, that's fine. Small, medium-sized companies, they're actually very flexible in terms of getting machine data. Part data, they're more sensitive, but if it's a machine data, go ahead. I mean, if they can get this kind of dashboard for them, yeah, why not, right? So that's what we're doing. It's not only the welding company. This is hydroforming company. They manufacture bellows like this. Like they make the bellows for Volvo, right? So basically, you have the engine, you have the muffler, and then you have the bellow in between, right? And then you have a rigid part, and then you have a stationary, more moving mufflers, right? You have to have something in between that compensates all the motion. So that's what the bellow does, right? So and then what they do is sometimes they get failures because it's hydroforming. You have pressure inside, and then you have crimping to make those bellows. So can we actually predict how many bellows are being made? They have many different bellows. Depending on the part design, they will do 20 times or 30 times and so on. So can we calculate how many times they're doing? So that's what we did. Again, we built this kind of dashboard, gave it to the company. They were happy. They want to put more sensors on different hydroforming machines. This is an example of a plasma cutting. You can see the sensor on the machine like this, and then here the plasma, knowing the actual cutting time is actually important, right? Because the nozzle wears down, so you need to change it. So that's what we did. Can we calculate the exact cutting time just from the sound, right? And then the interesting thing is you can actually tell the difference when it wears down. So you can calculate, hey, it's 70%, 60%, oh, you need to change the nozzle, and so on. Before, they will just run it until it fails, and then they will change the nozzle and so on. But you can calculate exactly, and you can also predict. So you can develop dashboards like this. How many parts been generated? Is the nozzle condition? How good is it? And so on. So that's what we've been doing. So I'm working with many different manufacturing companies locally around Purdue. So I've been going to different companies, talking to them, dealing with them. Hey, can we put our sensor on your machine? We have funding from Lilly Endowment. Basically, it's a big pharmaceutical company. They give big funding to Purdue to help support the manufacturing companies within the state of Indiana to have more IoT capable, right? We'll get closer to Industry 4.0, right? In the beginning, when you go to these manufacturing companies, they're not even IoT Industry 3.0. They were like Industry 1.0, 2.0, right? They don't even know, a lot of them didn't even know what IoT was and so on, right? So but they want to know. Now there you have the reshoring happening. You have workforce shortage, so they need to automate, they need to optimize their plant. But so they're actually seeking help from Purdue to be able to do that. So that's what we're doing, trying to help the companies to be able to get more data from the companies and so on. So I want to change my topic slightly to the human aspect, right? So you have the data from machines. How do we actually get data from humans, right? And how do we get human skills digitized so that we can actually develop AI models to replace the human skills so that we can use that for robots and stuff like that. So you have the Industry 4.0 is actually communicating, being able to talk to machines and so on, right? Getting data, using AI for machines. But Industry 5.0, they're already talking about it, is when humans can actually communicate better with machines and how human plays a role within the manufacturing floor is important, and that is considered the Industry 5.0. So you have the machine automation side, you have the human side, you have the autonomy side. Can we combine all of that? So you need to build a platform or a framework for that. So what we're trying to do is, okay, can we get human to collaborate or communicate with the robots or machines in a virtual environment remotely, so that you can actually work with the machine anywhere, right? And then be able to get trained, be able to train the robot, and things like that. So then you need to be able to get data from the robot, be able to replicate that in the virtual environment, and then we're using VR or display or haptic robots to be able to interact. So VR is just one example. So this is an example of the virtual space. I have two physical robots that are connected to the virtual machines, right? And then you can interact with the robots here in the virtual space, but it is connected to the physical space. So if you move it in the virtual space, physical machine will actually move. So you can interact. So this is an example of once it is in virtual space, you can actually do a lot of things. This is just doing, hey, robot, follow the ball, right? So you can actually do different manipulations, training, and robots, and so on. So this is an example of using a collaborative robot to manipulate the actual physical robot. So you can see once the student moves the collaborative robot, the physical robot moves like this. But then he does it, it's side by side, but he does it in the virtual space, so that robot can be remotely somewhere else as well too. So this is robot manipulation in the simulation space. You can do easily training of the robot This is a example of robot to do pick and place, train that in the virtual space, and then once it gets trained in the virtual space, in the physical space, the robot can do it as well too. So this is the example of pick and place. So here is teaching part how, you have different parts, different shapes, right? Where to put it. And then we have developed AI models for the robot to find out, you have a bunch of parts there. How do you know which one's which, right? You have different colors, different shapes. Robot has to find out which one is when you look at it, okay, that's this shape. So you have the AI model trained for that. And also figuring out which one is easier to pick up, right, from the top. So you need to figure that out. So, on manufacturing floor, you have a bin like this. This is a small, medium-sized companies, right? It's a casting company. You have parts like this, right? When I went there, basically you have a part like this that needs to be machined. So an operator will stand and put that out of the bin, put it on the CNC machine, get it machined, put it on another bin. All day, that's what the operator is doing, right? But can we actually put a robot there and automate that? But that's not as easy because it's how do you actually pick it up, right? It's not easy to pick up. So, but what we're trying to do is, but humans know, if you put a human there, without any experience, we'll know which one to pick up first, how to pick it up first, right? Robot doesn't know. So can we actually, digitize the human skills? It's a simple skill with figuring out which one to pick it up, which one to, how to pick it up. So we have trained using the human skills, right? So what we do is have the human take a photo of the part, right, and say, this is a pickable part. Have a photo, and that's not a pickable part. So kind of teach the robot saying, when you see a part, okay, that's a pickable, so go and pick it up. Right? Can we actually get the robot to train? So that's what we did. I'm not going to go through the details of how we did it, but basically we took many photos like this, right? And then, so that's the human skill, knowing which one is a pickable part. And then take photos, train the robot first. So this is an example of that. So you have a human, my student just taking photos at different locations, say, hey, these are pickable parts. But for AI models to work, you need thousands of data. And if I try to get my graduate student just take photos 1,000 times for bin, he's gonna complain, right? So say, okay, how can we get initially do the training for the students and have the robot learn by itself? So we did it like 200 times, right? And then robot goes try to, things that the robot learned, the robot tries to go there, take a photo, and try to pick it up. And if it succeeded, then you have another data point. If it failed, then you have another data point of failure. So robot can actually continue to collect data and learn more. So this is an example of robot getting data. So you go there, pick it up, okay, that's a success, right? And then goes to another part, okay, and then it scans, I think I can pick it up, and go and try to pick it up as well. So that photo, it was a failure, so that gets added to the data. So it does the self-learning like that. So this is an example, right? Initially, with the human inputs, human training, it was around 70% success rate. And then the robot did the relearning by itself. We got it up to 90% success rate. So after 90% success rate, the robot is trying to pick it up automatically. So while it's doing automatically, it's actually collecting data. So it's actually taking data over and over again and learning by itself. And why is it that we can only go up to 90% success rate? Is because the part is not flat, right? It's three-dimensional, so the robot has to come in three-dimensional directions. So that what we did was, okay, let's have the robot to come in 3-dimensional directions. And then we have a LiDAR figure out which orientation the robot has to go in. So we have some physical modeling into this. Then the success rate went up a lot more as well too. So this is an example of a 3D part handling, right? Again, initially you train the model and say, hey, there's a pickable part. When you see it, this is the direction that you should go into. Okay. Again, that's the direction, right? So you try to find the normal surface, right, and then find the direction, right? So you train the robot that way. And then same thing. After about 200 data, we have the robot to learn by itself, get more data, get trained a lot more data, and so on, right? And then once it's been trained, right, we have the part going in the normal direction so that it knows which way to come in. So this is an effort to have the human skill incorporated into training and learning of the robot and how humans interact. So we are trying to have the robot interact more with humans, both in a physical space as well as in the virtual space as well too. So another application that I'm working on is, when you have it's in an airplane, you have the seam, and they do the seam sealing, right? But humans actually put the seam sealants, and then they want to automate it with robots. It's like you have, we do sealants on, like, in our kitchens and so on, right? On an airplane, it's curved surfaces. You need to put a sealant on, right? Can we get the robot to do it? How do we get the robot to know the depth, direction, what path? Can we get the robot to be trained in the virtual space and so on? So that's what I'm trying to do as well. So I work in manufacturing. So value is, I want to be able to help small and medium-sized companies so that the value is added to the companies as well too. But the value has to be there for me as well too, right? So one of the things that I did was, I'm working a lot and I need to relax. And this is a rocking chair. I wanted to have a rocking chair like this, right? But being a manufacturing researcher, can we actually make it? This is a famous Sam Malouf's rocking chair. He passed away, I think 15 years ago. When he was alive, that was like $40,000. It's all handmade. There's one in the White House. That was President Ronald Reagan. He donated to the White House. So he passed away. It's a lot more expensive, right? So what we wanted to do is, but he opened the design to the public. So if you want to copy, you can copy, right? It's all the hand skills. So not everyone can actually copy, right? So what we did was we did the reverse engineering, right? Can the manufacturing be used for myself, right? So I didn't do it. I have it with the student, but here's the 3D model of the chair. Get it CNC machined. You need a big router and to be able to machine that, and we didn't have it. So we actually looked for a router, and there was high school in the with the router. Woodworking classes, right? They have that, but then that's not being used anymore, right? So not many students are not that interested in the woodworking. So it was just sitting there and it wasn't working. So we said, okay, we'll fix it for you. Can we use that? So the school said, yeah, please do. So that's what we did. We got the machine. We did all the machining. And here's the rocking chair in my office, right? And here's me getting ideas sitting in that rocking chair, right? This rocking chair, I did it with the student. It's a sort of a term project. Student was so into woodworking, he wanted to build it. I said, yeah, let's do it. And he kept asking for wood. So it turned out that the department chair saw this and said, hey, I want a rocking chair like that. Why do you have one, right? So he said, well, you got to talk to the student. And the student got $1,000 from the department chair when he made one. And it turned out that he made a few more for his girlfriend and for his father and so on. So I don't know how many he made, but he just kept asking for wood. So it was value added for me, but as well for my student as well too. But anyways, Thank you very much for your attention. That was my research topic. If you have any questions, I'll be happy to answer any questions.
Okay, so now your turn. So please feel free to ask any question to Dr. Jun.
Yep.
When you're using the LiDAR to detect how to approach different objects to pick them up,
Yep.
is that are you using photogrammetry for that, or how are you processing LiDAR information?
Well, LiDAR gives you the depth information, right? So you have the surface information. We find the top surface and find the normal, and then we try to go along the normal directions.
So when you're talking about accessing manufacturing machines virtually, could you also use the LiDAR machines to generate a model using photogrammetry, so that way the person virtually can look at what's in workspace as well?
You could do that as well. LiDAR works with many data points, and it becomes slow and so on. But yes, certainly you can do it, but it's going to require a lot of computational power. And then the cost will go up and so on. But yes, certainly you can do that. Yep.
When training the software using the sound to train the software to identify different processes.
Yep.
Instead of if you didn't have an experienced operator, could you use the proprietary software and train it that way and eventually stop paying for it?
So proprietary software meaning you have a database with so many different sounds?
Yeah. So you could purchase the software.
So the software is, yes, so software is to get the data from the controller,
Yes.
Right? So that's a very good point. What we wanted to do was we want to use the data to automatically label the sound so that it gets trained automatically. So that's one direction that we're going, because it's a lot of work to be able to listen to each sound and say, this is that sound, that's the sound. The student actually chops up the sound and then categorize it in different columns and use that to train. And that's a lot of work. So there has to be some automation for that. So we're working on the automation, and yes, we're using that. But not all the manufacturing companies have that kind of software. So we actually had to buy it from Purdue and give it to the manufacturing company. But what interesting thing was, so the vendor, a manufacturing company, the equipment manufacturer, does not allow you to buy the software if you do not own the machine. And I try to buy it from Purdue, but I don't have the machine, right? It's the company's. So we had to go through a lot of different hurdles to be able to actually purchase it. But yes, that's what we're doing. Yep.
You highlighted that you use LiDAR to make the machine go into three-dimensional space to get data from it. We had a discussion 2 days back in our session in the class, which says that LiDAR is a costlier thing than a camera.
It's slightly more costly than camera. Yes.
So, what difference in accuracy do you get if you just use camera and if you just use LiDAR?
You can get depth cameras with two cameras. You can get depth information that way as well too. LiDAR gives you more depth information, and then depending on the quality, the price of the LiDAR as well. Bad thing about LiDAR is you need some distance as well. So that's one bad thing. Camera, you can get closer, but there's certainly advantages and disadvantages, but you get more depth information with LiDAR. Yep.
So if I'm remembering correctly, when you were talking about your neural net architecture for listening to the sounds the machines were making, did you say you were using a fully connected and a convolutional in combination?
For many of them, yes.
So could you talk a little bit about why you chose that architecture, and have you looked at anything like an RNN, considering like a
So yes, so to be able to listen to the entire, when you have within the sound wave file, you have many different events, and we want to be able to listen to the entire thing and be able to figure out the sequence of sound. RNN will be better. We're using actually LSTM for that as well. Or CNN is for classification each sound segment. Is this idle, is this operation? So it's a classification example. So we use CNN for that. You would take that sound and then train the CNN model to detect that sound. So you have a time window that is just propagating through the sound, and then within that time window, say whether it's 2 seconds and 1 second. This time window, this is idle population, so that's what we're using CNN for that. Later on, we want to be able to listen to like 1 minute segment and find out what's going on within 1 minute. We'll be using RNN or SDM. Yep.
So you were using conditional variation autoencoder in one of your slides.
Yep.
So where are you using it exactly?
We want to be able to, so when you use so you have a safe, we're working on a sort of what's called fingerprint technology. So we listen to the machine, like early morning when machine operator comes in, they do the warm-up test. So you do the warm-up, and every warm-up is the same. So you do the motion of each. So you listen to that warm-up sound, and every day you listen to it, and something will be different, right? So using the autoencoder, you listen to the sound, and then you can reconstruct. And then when the reconstruction should be similar to the reference. If there's so much difference, then there's something wrong with the machine. So we try to compare the anomaly or detect the anomaly within the entire sound. So that's one of the reasons why we're using the autoencoder. Any other questions? Yeah, I guess, yeah.
Two questions. Good presentation. My first question is the sound sensors. When you're doing the implementation, are you using multiple sensors on the machine or a single sensor?
We wanted to know the locational impact of the qualities of the sound. If it's a single machine with a single frame, one sensor is good. But a lot of times the machines have big structure and then another big structure. Like you have the Z-axis structure, you have the XY axis structure. And then which are two different structure, right? So the sound propagates, but it doesn't actually go to the other structure. Then you need two sensors. So it depends. Initially, we wanted to put multiple sensors and try to see, but it's the same if it is in one monolithic structure. So.
An additional question?
Yep.
More or less political. So you talk about 4.0.
Okay.
How are we lagging behind the Germans, or are we above the Germans?
Like who are we? Are we talking about we as in small medium? We as in
the US?
in the US? I mean, compared to Germany or Japan?
Because that's where the 4.0 basically
That's
started.
right. Yeah. It has become political, right? I don't know. But anyways, so Germany, of course, they started 4.0. I visited Italy and Germany for small, medium-sized companies. If you look at medium-sized companies, they're much ahead. Big companies, maybe at par, maybe slightly lower, but small, medium-sized companies in US, they're much lower. They're way down there. So there's a lot of work.
So we need to do more work.
But there's a lot of funding in Europe to raise the companies in terms of Industry 4.0. When that word came out, they put a lot of money to have the Industry 4.0 capability in the companies. So they got funding for that. US, not so much yet, right? So that's what we need. And I know Washington, D.C. is talking about that a lot right now. How do we actually get the SMMs in terms of Industry 4.0?
Okay, so any other questions? Then let's give him thanks again.
Thank you.
마이크 되는 거예요.